Hi, everybody. My name is Jean-François Herman. I'm an associate professor of computer science with SCIT, a French graduate school of engineering located in Paris, France. Today, in this presentation, we'll see how to use Maple to learn elliptic curve cryptography. The outlines. In this presentation, we consider one of the fastest ECC curves, namely curve 25519. This curve was first introduced by Daniel J. Bernstein in 2005 and is now used in many applications. The curve is y squared equal to x cubed plus 4866662 x squared plus x modulo p, a Montgomery curve over the prime field defined by prime number p equal to 2 to the power 255 minus 19, and it uses base point x equal to 9. We use Maple to write a program in cryptography for a cybersecurity challenge and to solve it. An elliptic curve is given in the problem statement with one of its points. The first step of the challenge is to recognize the ECC curve used. There is a smart, straightforward method to recognize curve 25519. 2 points of this curve are computed. The first point is P1 with coordinates x1 and y1. The second point is P2 with coordinates x2 and y2. y1 and y2 are given in the problem statement. The second step of the challenge is to compute x1 and x2 given y1 and y2. x1 and x2 may or may not be unique. The third step of the challenge is to use the Chinese Remainder Theorem with points P1 and P2 to decipher a PDF file. So let's start with elliptic curves in Montgomery form. Before defining curve 25519, we give some basic theory on elliptic curves in Montgomery form. An elliptic curve in Montgomery form is defined by the following equation: by squared equal to x cubed plus ax squared plus x, where a times b squared minus 4 is different from 0. On the points of the elliptic curve, we may define point negation, point addition, point doubling, and scalar point multiplication. Let E be an elliptic curve over Fp. Point negation. Let P with coordinates x and y be a point on E. We define point negation of P as minus P with coordinates x and minus y. Point addition. Let P with coordinates x1 and y1 and Q with coordinates x2 and y2 be two distinct points on E. Then the point addition is P plus Q with coordinates x3 and y3. And this coordinates x3 and y3 satisfy these equations. Point doubling: if P is equal to Q, then the doubling point P plus P is 2P with coordinates x4 and y4. And these coordinates x4 and y4 satisfy these equations. Scalar point multiplication. We define scalar point multiplication as follows. Given a positive integer m, scalar point mp is defined by mp equal to p plus etc. plus p, m times addition of p. So now let us focus on curve 25519. Curve 25519 is the elliptic curve in Montgomery form with the following equation: y squared equal to x cubed plus 4866662 x squared plus x modulo p over the prime field defined by prime number p equal to 2 to the power 255 minus 19, and it uses base point x equal to 9. So here we have the graphical representation of this curve, the graph of curve 25519. The base point, P0, is the point with coordinates x0 equal to 9 and y0 equal to this number. Base point P0 can be found in the paper written by Bernstein or in several RFCs. Of course, this point belongs to curve 25519. 2 points of this curve are now computed, starting from this base point, point 0. The first point is P1 with coordinates x1 and y1. P1 is equal to 2 to the power 1972 P0. The second point is P2 with coordinates x2 and y2, and P2 is equal to 2 to the power 2014 P0. So we are able to compute the coordinates of P1. So all the details are provided in the Maple worksheet. We are able to compute the value for x1 and the value for y1. Okay. And of course, this point belongs to curve 25519. We are also able to compute point P2 with coordinates x2 and y2. The values for x2 and y2 are also given in the Maple worksheet. And of course, this point P2 belongs to the curve 25519. So y1 and y2 are given in the problem statement. So now we will have to compute x1 and x2, and from these values, we will be able to compute the key to decipher the file. So the problem statement is the following. So the problem is called Elliptic VX. It's part of the challenge Brigitte Friand. So let us consider the following curve: y squared equal to x cubed plus a x squared plus x modulo n, where n is the following number. Let P with coordinates x and y be a point of the curve. So x is equal to this value, y is equal to this value, okay? And let k1 and k2 be two positive integers. We define point k1 p with coordinates x1 and y1, and k2p with coordinates x2 and y2. And this point are such that y1 is equal to this value, y2 is equal to this value. So given y1 and y2, we'll have to compute x1 and x2, okay? And with this value, for x1 and x2, we'll be able to compute the key to decipher the PDF file. So the key is Z, and Z is equal to x1 modulo n, and also equal to x2 modulo n minus 1 divided by 2. The ECC curve used. So remember, an elliptic curve is given in the problem statement with one of its points. The first step of the challenge is to recognize the ECC curve used. There is a smart, straightforward method to recognize curve 25519. First, we recognize an elliptic curve in Montgomery form. Okay, y squared is equal to x cubed plus ax squared plus x modulo n, where n is equal to this value. We check that n is a prime number, so is prime n returns true. If we notice that n is equal to p, remember p is equal to 2 to the power 255 minus 19, then we can assume that the curve is a curve 25519. We can easily check that point P belongs to it. Okay. And so we check if y squared is equal to x cubed plus 4866662x squared plus x modulo n. And if it is true, then we can deduce that it is curve 25519. If we do not notice that n is equal to p, which is equal to 2 to the power 255 minus 19, then we can compute a with point p. A is equal to y squared minus x cubed minus x divided by x squared modulo n, and we find n a equal to 4866662, and the curve is curve 25519. Okay, so 2 points of curve 25519 are given in the problem statement. The first point is K1P with coordinates x1 and y1. The second point is K2P with coordinates x2 and y2. y1 and y2 are given in the problem statement. So the second step of the challenge is to compute x1 and x2 given y1 and y2. Be careful, as I said previously, x1 and x2 may or may not be unique. So the computation of point K1P, we know y1, and what we want to find is the value of x1. So we can issue this command in msolve this equation with modulo p, and we will get 3 roots, 3 solutions for x1. x1a, this value, x1b, this value, and x1c, this value. Hence, we get 3 points. P1a with coordinates x1a, y1, P1b with coordinates x1b and y1, and P1c with coordinates x1c and y1. For point K2p, we know y2. We want to determine x2. So we issue the same command, msolve the equation modulo p, and this time we get 1 root x2. We have the value for x2. Then we have 1 point p2 with coordinates x2 and y2. Among the 3 points P1A, P1B, P1C, we notice that point P1C, so the last one, is the point negation of P1 defined on page 18. So in fact, when we computed the value for the key, we choose, we have chosen K1P as minus P1 and K2P as P2. The third step of the challenge is to use the Chinese Remainder Theorem with point P1 and P2 to decipher a PDF file. So here we just have to issue this command, Chinese remainder of x1, x2, the values that we just computed, and the modulos, p and p minus 1 divided by 2. And then we get the key to decipher the PDF file. This is the key. See. Okay, so, okay. Okay, so let's have a look to the maple sheet. So we define prime number p, 2 to the power 255 minus 19. We check if this number is a prime number. It is the case. We have some information about its length. Okay. Base point P0 is defined as follows. You remember x0 is equal to 9 and y0 is equal to this value. So we check if this point, this base point P0 is a point of curve 25519. So we issue this command, and we can check easily that this point belongs to a curve 25519. So if so, the value for y0, as I said previously, can be found in the paper written by Bernstein, or in several RFCs, or we can compute it. Y0 is the value that we want to determine. So we issue the command msolve y0 squared minus x0 curved minus 48666 time x0 squared minus x0 modulo p, and we will get in fact two values, y0 and minus 10 y0 modulo p, and we find the same value for y0. Okay, so here we have the point doubling procedure. So we have a point P with coordinates x and y, and we compute P plus P. So 2P, the point with coordinates x4 and y4, and if you remember the computation of P plus P, we have these relationships between x4 and y4. So now we are able to compute P1. P1 is 2 to the power 1972 P0. So here we will have to iterate, and we are able to compute x1, this value, and y1, this value. We do the same thing for P2. P2 is equal to 2 to the power 2014 P0. So we will have to iterate a bit longer, and we are able to compute x2, so this value, and y2, this value. So now we have all the points that we need to write our challenge. Point P1 with coordinates x1, y1. So we can verify that this point is a point of curve 25519. We have the point negation of P1, x1 and minus y1 modulo P. We will use this point negation of P1 for KP in the challenge, KP1. And point P2 with coordinates x2 and y2. Again, we are able to check that this point belongs to the curve. So here, now we have all the points to write our challenge. In the challenge, we use n instead of p. We have n equal to p. The equation of the curve is y squared equal to x cubed plus a x squared plus x modulo n. The point P is a point of the curve, and we have chosen P as P1. So x is equal to x1 and y is equal to y1. If we notice that n is equal to p is equal to 2 to the power 255 minus 19. So the question to ask is it curve 25519? We checked with the coordinates of point P, and the answer is yes. Otherwise, we'll have to compute A. So we issue this command with msolve, the equation, and or we can also compute y squared minus x cubed minus x divided by x squared modulo n, and we will get the same value. A is equal to 4,86662. So we know that the curve is curve 25519. So now the points, K1P, you remember, we have K1P. Our K1P is not P1, it's it's minus P1. So that's why we have xy equal to minus no, y1 equal to minus 1 modulo n. And so what we want to determine is the value of x1, knowing that this point belongs to a curve 25519. So we issue this command with msolve, and we get these three values for x1, x1a, so this value, x1b, the other value, and x1c, the last value. Okay, so we have chosen K1p as the point negation of P1, that is minus P1. So the idea behind this is that if you see that y1 is minus 1 defined previously, then you have directly the answer for x. It's one of this answer. So you don't even have to compute x1 if you just notice that y1 is minus y1 defined previously modulo n. And okay, that's for point K1P. For point K2P, we have y2. We know y2. We want to determine x2. So again, we issue the same command, msolve y2 squared minus x2 cubed minus 4,86662 x2 squared minus x2 modulo n, and we'll get this value for x2. And we have chosen K2P as P2. So now we can compute three keys. Key1, if we take the first value for x1, and we will see that Q1 is the wrong key, it doesn't work. And you can compute key 2 with the second value for x1. Again, it's the wrong key. And the key 3 is the value, you can compute key 3 with the third value of x1. And with this value, you are able to decipher the PDF file. Okay, that's because we have chosen KP1 as minus P1. Okay, I think that's all. Thank you for your attention.